Right, and we are back again. Hopefully you've had a chance to sit the assessment I set you last week. Hopefully you've had a chance to look at the video where I walk you through the assessment and you've corrected it start to finish, and hopefully you're feeling confident about it. If you're not, send me an email with any of the questions you're still not sure of and I will sort that out. Today we're starting a new topic. This is a topic of sound. The video for this lesson isn't really going to be that long. This is more of an introductory lesson, but you've got more in the form of worksheets that I've sent you this week. So by the time you've done the video and the worksheets, that should be about your 2 hours before Wednesday. So let's have a look at the learning objectives. Learning objectives. I can explain what causes sound and how to make sounds louder. And we can explain the link between frequency and pitch. So we're going to do that, and I'm going to use this little fella here to sort of help me out. Now, you've all seen a guitar before, obviously, and if I want to make a sound on the guitar, we know that I'm going to pluck one of the strings, but let's examine a little bit more closely what's happening if I actually pluck one of the strings. I'm bending the string down with my thumb, and then when I let go, the string is doing that. It's bouncing forwards and backwards. We have a word for that. You may be used to the word vibrate, especially from the topic with solids, liquids and gases when we were looking at particles and solid vibrating. So we could say that the string vibrates. You're going to have to start recognizing the word oscillate as a word which means vibrate. So when I pluck that string, yes, it vibrates or it oscillates. Now, why does that cause sound? Well, when that string vibrates, the air around it, as it bashes into the air around it, also starts to vibrate, starts to oscillate. And those air particles that are now vibrating bang into the air particles next to them, which cause them to vibrate and oscillate. And this energy spreads out. It's a wave. It's called a longitudinal wave, and we're going to come on to that more in the next video. But it is a wave, and sound spreads as a wave. Now, it doesn't just have to be in the air. If I was to put my ear to the wood of this drum and rattle my fingers on the other side of the drum, I can hear that extremely loudly, more loudly, in fact, than I'd be able to if my ear wasn't on the, I said a drum though, it's a guitar, isn't it? If my ear wasn't on the guitar. Because sound actually travels better through solids than it does through the gas or through air. It travels better through solids than it does through liquids. And that's because when these particles are vibrating or oscillating and banging into the particles next to them, in a solid, particles are arranged closer together. So when they vibrate, it's easier for them to bang into something next to them. So essentially what I'm saying is, to create a sound, we need to have something that's vibrating or oscillating. Now, you might think, well, I can make sounds without on a guitar without oscillating a string or vibrating a string. We talked about banging the wood before. Well, when we bang the wood, we are causing the wood to vibrate. The wood is then causing the air around it to vibrate. When I'm speaking now, if I was to put my, you do it, put your fingers on your throat there and make a humming sound like that, you can feel your voice box vibrating, which vibrates the air around it, creating a sound. So sound is caused by vibrations or oscillations. So how do I make those sounds louder, and how do I affect the pitch? Well, loudness is fairly straightforward. If I have a string here and I pluck it, I don't even know if you could hear that through the microphone. I've plucked it gently and it's only vibrating. It's not going out very far, if you like. I'm going to use the word amplitude later on, but for now it's not vibrating very far either side. But if I really push it further with my thumb, then it's suddenly much, much, much louder. See, when we look at sound, the amount that it's vibrating, how far it's going either side, is going to be really, it's going to have a massive effect on the volume. The more it vibrates, the louder it's going to be. I could get the same effect with a ruler. If I put that on a desk and twanged the ruler, if I only twanged it a little bit, so it was bouncing up and down a little bit, it will be very quiet. If I absolutely smashed it and it was bouncing up and down like that, it's going to be a lot louder. So the amount of energy I put into the vibration, the size of the vibration, is going to be linked to the volume. But what about that other learning objective, pitch and frequency? Well, again, if I was to play you two notes, you absolutely would be able to tell the difference between them. I could play you that sound, or I could play you this sound. And if I asked you which was the higher note, you'd say the second one, and the first one would be lower. Now, why is that? Well, the first one is, well, first of all, the first one's lower, so we say it's got a lower pitch. So when we talk about pitch, we're just talking about, does the sound high or does it sound low? That's what pitch means. But pitch is linked to something called frequency. And when we talk about frequency, we're talking about how fast those vibrations occur, not how far out they go, which would have been the amplitude, remember, that's linked to volume, but how fast they go. And if something has got a high pitch, right, like this, remember, high pitch. If something's got a high pitch, then it's vibrating very, very fast. A low pitch is not vibrating very, very fast. And that's where we use the term frequency. If I asked you, just forget science, but in the English language, what does frequency mean? You know, you might think about frequency describing how frequently something happens, right? And in this sense, that's exactly what it's doing. It's describing how frequent the vibrations are, how often the vibrations are. So if you've got a high frequency, you're going to have a high pitch. And we measure frequency in a unit called hertz, and it really tells us the number of waves per second. So when we measure a sound of 440 hertz, that's 440 vibrations a second. So before I go to the textbook page and we look at some more, just a recap of the main things. To create sound, we need a vibration. Wherever the sound is coming from, a vibration is causing it, even if it's not necessarily obvious to you to start with. And if you've got some ideas of sounds and you don't know what the vibration is that's causing it, drop me an email and I'll explain it to you. But essentially, vibrations cause sounds. The larger the vibration, right? In other words, the larger the amplitude, but we'll get to that word amplitude next lesson, the louder it's going to be. And the higher the frequency, the faster the vibration, the higher the note is going to sound. So let's have a look at the textbook and see if we can pick up some more words and maybe have a look at one or two of the questions. So it's the words in bold that I'm interested in. Now, you've seen this first paragraph here. It refers to volume as being intensity. Now, I have taught you about the volume of a sound is to do with the amplitude, how far out that vibration is going, and that will all come next lesson. But I want you to be able to recognize the term intensity as being linked to volume. If you've got a high intensity, you have a high volume. We can see pitch there as well, which we've already talked about. The faster the vibration, the higher the pitch, the higher the frequency, the higher the pitch. Frequency is mentioned here, and this is how we would spell the unit of frequency, the hertz. And it does say here, vibrations 400 times per second will be a frequency of 400 hertz. Now, the human ear can usually hear, or its widest range when you're born, is between about 20 hertz and 20,000 hertz. So we do get a big range of frequencies with sound. Now, this word here, the amplitude, I mentioned that before, and equally it says here that that's linked to the volume of the note. Until you start to look at how the sound wave looks, it's going to be very difficult for you to imagine what the amplitude is. So just for now, just have that word kept in your head, that amplitude is linked to volume. And next lesson we'll really clarify what amplitude actually means. So don't panic if you don't get that now. Although it is essentially just how far out it's is it vibrating a little bit or is it vibrating a lot? But we'll get to that next lesson. All right. So let's have a look at some questions here. Question 1. I'm sure you don't need my help to come up with 4 animals that make loud sounds. Question 2, though, I'm hoping that you by now you know what a vibration is, and you've got that word oscillation in your head as well. We know that we can use the word oscillation instead of vibration. It's something that's moving side to side. Yeah, that's it, essentially. Question 3 is an interesting one. A tuning fork vibrates 500 times a second. What is its frequency? Well, its frequency is going to be 500 hertz. But I'm going to give you an equation that we are going to use going forward for that. How do I calculate the frequency if, for example, it said 500 times in 10 seconds and not per second? I'd need some kind of way of working it out. So the equation we use to work out frequency is the number of vibrations divided by the number of seconds. So the number of oscillations, the number of vibrations, or even the number of waves it may sometimes be presented to you as, divided by the time. So here we've got 500 vibrations, we've got 1 second, 500 divided by 1 gives us a frequency of 500 hertz. Question B, how will something with 500 hertz sound different from a tuning fork that vibrates 300 times per second? So how would something with a frequency of 500 hertz sound different from something with a frequency of 300 hertz? Well, 500 hertz is obviously the higher frequency, so therefore it's going to be a higher pitch. It's going to be a higher sounding note. Okay, hopefully you get that. There's not a great deal more really to look at here. You know, it's just some animals making loud noises, so you know, enjoy that. Now let's have a look at some slightly harder questions. And this will use the equation we've just talked about. A giant hummingbird flaps its wings 12 times per second, and bee hummingbirds can flap at over 80 times per second. Explain how the noise made by the wing of each species will sound different. Actually, this one doesn't use the equation, sorry. So the giant hummingbird, if it only flaps its wings 12 times a second, it's a frequency of 12 hertz. The bee hummingbird, if it flaps it 80 times a second, that's 80 hertz. It's a higher frequency. It's going to be a higher pitch sound. We're not going to talk about volume. We haven't got the information in the question to know which is going to be louder. We just know it's going to be a higher pitch note, not necessarily a louder note. So don't assume that higher pitch equals louder. It's not true. Two male gorillas are beating their chests. One makes a lower sound than the others. Suggest what this could tell you about the two gorillas. Oh, interesting. Now, if one of them is making a lower sound, then that means that the sound waves that are coming off that object, off the gorilla's chest, are going to be of a lower frequency. So when they bang their chest is going to vibrate at a lower frequency, less times per second, to give us that lower note. So what does that tell us about the makeup of the gorilla? Well, let's have a look at guitar strings for that. If I play a low note on this string here, right, or a high note on that string there, I can see that the lower notes, the ones that vibrate less, are the thicker strings. They are bigger. And it does seem to be the case that, you know, if I bang this desk, you know, I get a low pitch sound, a low thud. Big, heavy objects tend to vibrate more slowly when they are hit. They tend to give you lower pitch sounds. So if I've got two gorillas and one of them has a lower pitch sound, he's probably going to be a bigger gorilla. All right. Question B. How can one of them make a louder sound than the other? Well, this is irrelevant to the pitch. Right. You can have a high pitch that's quiet or a high pitch that's loud, and vice versa. So how can one of them make a louder sound? They can hit themselves harder. Would be that would be the answer. You hit yourself harder, you're going to be the answer. That will make you louder. Sorry, I'm just waffling now, because it's going to create vibrations that are bigger. Okay, you're putting more energy into the system as well. You're going to create bigger vibrations if you hit yourself harder. It's like playing a drum. You know, if you're tapping away at a drum, you might get a sound from it of a certain pitch. You whack the drum, the pitch doesn't change, but it becomes much, much louder. And just to back up what we said before, you get a bass drum, you thud a bass drum, the big ones, and they are a very low sound, just like the big gorilla, because the bass drums are so big. So essentially, all I want you to take from this are the idea that it's all about vibrations, and that the faster the vibrations, the higher the frequency, therefore the higher the pitch. And if you put more energy into that vibration, you pluck that guitar string harder, you hit the drum harder, you can make those vibrations bigger. Now that won't change the pitch, but it will make something louder. And next lesson, we'll get more into the actual structure of the sound wave itself. That word amplitude will start to make a lot more sense. Bye-bye.